Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to cover chapter 11 for our MCAT Organic Chemistry playlist, and this chapter is titled Spectroscopy. This chapter is going to introduce three major techniques that chemists use to understand molecular structure by analyzing how molecules interact with different types of electromagnetic radiation. Therefore, in this chapter, we're going to explore the following objectives. We're going to begin with infrared spectroscopy. This focuses on how molecules absorb infrared light to undergo bond vibrations such as stretching and bending. These vibrations give rise to characteristic absorption patterns that are going to help us identify specific functional groups. Then we'll move into ultraviolet visible spectroscopy, where we're going to explore how molecules absorb ultraviolet light to promote electrons to higher energy orbitals. In particular, we're going to look at how conjugated systems shift absorption to longer wavelengths. Finally, we'll finish with nuclear magnetic resonance spectroscopy, or NMR, with a focus on proton NMR. This technique reveals the unique chemical environments of hydrogen atoms in a molecule, and it's one of the most powerful tools for determining molecular structure. With that introduction, let's begin with defining spectroscopy. Spectroscopy is the study of how light interacts with matter. More specifically, it refers to the absorption of electromagnetic radiation by a molecule in discrete amounts, which correspond to the energy difference between two quantized states. Molecules, they can only occupy certain allowed energy levels, not anything in between. So when the energy of incoming radiation matches the gap between those levels, then the molecule absorbs that energy and undergoes a transition. The type of transition depends on the type of radiation used. So in this chapter, we'll be focusing on three. The first is vibrational transitions that are observed in IR spectroscopy, and they occur when a bond absorbs infrared light and begins to vibrate more energetically. The second is the electronic transitions that are seen in ultraviolet visible spectroscopy, and they occur when electrons are promoted from lower to higher energy orbitals. Finally, we will look at nuclear spin transitions, which take place in magnetic fields, and they are the basis for NMR spectroscopy. Now let's turn our focus to infrared spectroscopy, or IR spectroscopy. This detects molecular vibrations, which are periodic motions of atoms within a molecule. These include bond stretching, where atoms move closer or farther apart along the bond axis. And they also include bond bending, where the angles between atoms change. Many molecules also exhibit more complex vibrations that are combinations of these basic motions. Each type of bond is going to vibrate at a different frequency depending on the mass of the atom and the strength of the bond. But a bond will only absorb IR light if the energy of the radiation matches the energy that's required to excite that vibration. So each bond has a characteristic absorption frequency, and this gives us a unique way to identify the types of bonds present in a molecule. To see why this works, let's place IR radiation in context. So on the electromagnetic spectrum, infrared light lies just beyond red light in the visible region. It has longer wavelengths and lower energy than visible light or ultraviolet light. So this means it's not energetic enough to excite electrons or cause ionization, but it is just right to induce vibrational transitions in covalent bonds. Now let's return to that key quantum idea that molecular energy is quantized. Molecules don't have a continuous range of vibrational energies. They have discrete energy levels. So when infrared radiation is absorbed, it's because the photon's energy matches the energy difference between two vibrational states, and this is commonly referred to as DeltaE. If there's no match, then the photon simply passes through. Because DeltaE is different for every bond type, and it is determined by both bond strength and the atomic masses involved, each bond will absorb a different frequency of IR light. So for example, a carbon double bonded to an oxygen, that's going to absorb a different frequency than a carbon single bonded to a hydrogen atom. And that's because their vibrational energy levels are spaced differently. So this is what IR spectroscopy detects: changes in vibrational energy levels. So when we pass IR radiation through a compound, we're probing all of the bonds in the molecule. If the light contains a frequency that matches a vibrational transition, that frequency is absorbed, and then we detect that absorption. But if the frequency of the radiation doesn't match any of the allowed vibrational transitions, then the light passes through without being absorbed. So by recording which vibrational transitions are allowed, by recording which frequencies are absorbed and how strongly, we can identify the types of bonds that are present in that molecule or compound. The output is an IR spectrum, which is a graph showing how much light is absorbed at each frequency. And this lets us determine which bonds are present in the molecule. Now, instead of plotting frequency directly, IR spectra are reported in terms of wave number, which is the reciprocal of wavelength, and it's measured in inverse centimeters. Wave number is directly proportional to energy. So higher wave numbers correspond to higher energy vibrations. The standard IR region ranges from about 4,000 to 400 wave numbers. This range covers almost all useful vibrations for common organic functional groups. And when you examine an IR spectrum, what you're really looking at is a plot of percent transmittance versus wave numbers. So a dip in this spectrum, or a peak, indicates a frequency where light was absorbed, meaning a vibrational transition occurred. So for example, a sharp absorption near 1715 wave numbers typically indicates a carbonyl stretch, while an absorption near 2900 wave numbers is associated with a carbon-hydrogen stretching. Now that we've built a foundation for understanding what IR spectroscopy measures, we're ready to explore the finer details. So in the next part of the lesson, we're going to look at specific types of molecular vibrations, how to interpret peak position, intensity, and shape, and also how to recognize the characteristic absorptions that correspond to different functional groups. To start, we want to reiterate that when a molecule absorbs IR light, the energy causes the atoms in the bonds to vibrate. And these vibrations can take a few different forms. The simplest is bond stretching, which can either be symmetric, where both atoms move in and out together, or asymmetric, where one atom moves in while the other moves out. Bonds can also bend, which involves changes in bond angles. These bending motions can also be symmetric or asymmetric, and they're especially common in molecules with 3 or more atoms bonded to a central atom. These vibrational patterns are what give rise to the absorption signals in an IR spectrum. But to fully interpret those signals, we need to consider 3 main characteristics: wave number, intensity, and shape. Let's start with wave number. As we mentioned earlier, this refers to the position of a peak on the x-axis of an IR spectrum. It tells us the frequency of the absorbed light, and it's directly related to the energy of the vibration. The wave number at which a bond absorbs is determined by 2 things. The first thing is the strength of the bond, and the second thing is the masses of the atoms involved. Stronger bonds and lighter atoms are going to vibrate at higher frequencies and therefore absorb at higher wave numbers. So for example, if we're comparing a carbon-hydrogen single bond to a carbon-carbon single bond, a carbon-hydrogen single bond is going to absorb at a higher wave number than a carbon-carbon single bond. Next is intensity, which refers to how strong or tall a peak appears on the spectrum. Some peaks are very pronounced, while others are faint, and this depends on how effectively a particular bond absorbs light. Bonds with a larger change in a dipole moment during vibration, like an oxygen-hydrogen bond or a carbonyl bond, they tend to absorb strongly. This is in contrast to bonds like a carbon-hydrogen single bond, which undergoes smaller dipole changes and may show weaker absorptions. Finally, we consider shape. Some peaks are very sharp and narrow, while others are broad and rounded. This shape depends on several factors, including hydrogen bonding, which can broaden peaks significantly. So for instance, a oxygen-hydrogen stretch in alcohols typically appears as a broad signal due to intermolecular hydrogen bonding. So with these characteristics in mind, we can now divide the IR spectrum into 2 main regions: the diagnostic region and the fingerprint region. Below 1500 wave numbers is the fingerprint region. And this part of the spectrum, it contains a dense collection of peaks from complex bending vibrations to skeletal motions of the molecule. And while it's difficult to analyze on its own, the fingerprint region is unique for every molecule, so it serves like a molecular barcode, and it's often used for confirming a match between known and unknown samples. But we're not so concerned with this region for the MCAT. The region that we are concerned about for the MCAT is the diagnostic region, and this is from about 4,000 to 1,500 wave numbers, and it contains most of the important and easily interpretable signals. Here we see absorptions from functional groups, and these peaks are typically strong and distinct, and they allow us to identify specific bond types and functional groups. So with that being said, let's now take a look at some of the most important characteristic absorption ranges that appear in the IR spectrum. These ranges allow us to quickly identify functional groups. Alkanes show carbon-hydrogen stretching in the region of 2,800 to 3,000 wave numbers, and carbon-carbon single bond stretches that typically appear around 1,200 wave numbers. Alkenes exhibit carbon-hydrogen stretching for double bonded carbons between 3,080 and 3,140 wave numbers, while the carbon-carbon double bond stretch appears near 1,645 wave numbers. Alkynes show carbon-hydrogen stretching for triple bonded systems around 3,300 wave numbers, and carbon-carbon triple bond stretches are found near 2,200 wave numbers. Aromatic rings display carbon-hydrogen stretches in the range of 2,900 to 3,100 wave numbers, and carbon-carbon bond vibrations between 1,475 to about 1,625 wave numbers. Alcohols have a very broad oxygen-hydrogen stretch that's caused by hydrogen bonding, and it's typically observed between 3,100 to 3,500 wave numbers. Ethers show a carbon-oxygen single bond stretch that falls between 1,050 and 1,150 wave numbers. Aldehydes display a strong carbon-oxygen double bond stretch in the region of 1,700 to 1,750 wave numbers, and then they also show a distinct oxygen-hydrogen stretch where the hydrogen is bonded to the carbon of the carbonyl group between 2,700 and 2,900 wave numbers. Ketones show a strong carbonyl stretch, which appears in the same range of 1,700 to 1,750 wave numbers. Carboxylic acids display two major signals: a broad oxygen-hydrogen stretch from 2,800 to 3,200 wave numbers, and then a carbonyl stretch around 1,700 to 1,750 wave numbers. Amines exhibit a sharp nitrogen-hydrogen stretching signal that's typically found between 3,100 and 3,500 wave numbers. So, all of this information is really important to be familiar with. So by memorizing these regions, or again, getting familiar with the most prominent ones, you'll be able to look at an IR spectrum and quickly narrow down the possible functional groups that are present in a molecule. And that pretty much brings us to the end of our discussion on infrared spectroscopy. We've explored how IR radiation causes bond vibrations, how those bond vibrations appear on a spectrum, and how to interpret the position, intensity, and shape of the peaks to identify functional groups. Now we're ready to move into the second objective, which is all about ultraviolet visible spectroscopy, or UV-Vis for short. UV-Vis spectroscopy is used to study how molecules absorb ultraviolet or visible light. And this type of light carries more energy than infrared, and instead of making bonds vibrate, it actually causes electrons in a molecule to become excited. That means they jump from a lower energy orbital to a higher energy one. To collect a UV spectrum, we shine ultraviolet light through a sample, and usually the sample is dissolved in a clear solvent that doesn't absorb UV light, so that the absorbance we measure comes only from the molecule we're interested in. As the light passes through, we record how much is absorbed at different wavelengths, and this produces a graph called a UV spectrum, which shows absorbance on the y-axis and wavelength on the x-axis. One important feature of the spectrum is something called lambda max. This is the wavelength where the molecule absorbs the most light. But why does absorption happen at all? It's because of the electrons in the molecule. Molecules that have pi electrons, which are electrons found in double bonds, or non-bonding electrons like lone pairs on oxygen or nitrogen, those can absorb UV light. And when they do, those electrons are promoted to a higher energy orbital, specifically to something called an anti-bonding orbital. Whether this promotion happens at a shorter or longer wavelength depends on how much energy is needed to excite the electron. And that depends on the energy gap between the lower energy orbital that the electron starts in, called the HOMO, or highest occupied molecular orbital, and the higher energy orbital it moves into, called the LUMO, or the lowest unoccupied molecular orbital. If the gap between the HOMO and the LUMO is small, then only a small amount of energy is needed to excite an electron from the HOMO to the LUMO. That means the molecule can absorb longer wavelengths of light, which have less energy. On the other hand, if the energy gap is large, then it takes more energy to excite the electron, so the molecule absorbs shorter wavelengths which have higher energy. One very important factor that affects this energy gap is something called conjugation. Conjugated molecules have a series of alternating single and double bonds or connected p orbitals that allow the electrons to spread over several atoms. And this delocalization lowers the energy difference between the HOMO and the LUMO. So electrons in conjugated systems can be excited by lower energy, longer wavelength light. So when a molecule has a lot of conjugation, then this lambda max shifts to longer wavelengths. And this is called a red shift. In contrast, molecules without conjugation typically absorb at shorter wavelengths in the UV region. So to summarize, in UV vis spectroscopy, we shine ultraviolet light on a molecule and we watch how its electrons respond. Molecules with pi bonds or lone pairs can absorb this energy and undergo an electronic transition, moving an electron to a higher energy orbital. The amount of light absorbed and the wavelength of maximum absorbance gives us information about the structure of the molecule, especially about the presence of conjugated systems. And with that, we've completed objective 2. We're going to end the video here. In the next video, we will cover our third and final objective. I hope this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.